Hi, this is Arnav Varma. I'm pleased to present Transformers in Self-Supervised Monocular Depth Estimation with Unknown Genre Intrinsics. This is a joint work with Hemang Chawla, Bahram Zonooz, and Elahe Arani. Recently, transformer-based architectures have outperformed CNNs in image classification, object detection, semantic segmentation, and supervised monocular depth estimation. However, supervised monocular depth estimation methods require extensive RGBD ground truth collected from costly LiDARs or multi-camera rigs. Instead, self-supervised methods have increasingly utilized concepts of structure from motion to train monocular depth and eager motion estimation networks simultaneously. Note that these methods use CNN-based encoders and usually require ground truth camera intrinsics. Therefore, we first demonstrate how vision transformers can be adapted for self-supervised monocular depth estimation. To the best of our knowledge, this is the first work demonstrating the use of vision transformers for self-supervised monocular depth estimation. We additionally introduce a modular method for estimating camera intrinsics, that is the focal lengths and principal point. By modular here, we mean that this method works with both CNN as well as transformer-based architectures. Finally, we investigate the trade-off between transformer-based and CNN-based approaches in terms of performance on kitty depth estimation, robustness to corruptions and adversarial attacks, and runtime computational and energy efficiency. We will first briefly discuss the self-supervised monocular depth estimation framework. Given a set of images from video sequences, we train depth and eager motion networks simultaneously. The inputs to the networks are a sequence of consecutive RGB triplets. The subscript 0 corresponds to the current frame, and the subscripts -1 and 1 refer to the previous and next frames respectively. The depth network estimates pixel-wise depth of the current frame. The eager motion network, meanwhile, receives two image pairs as input, previous and current frames as one pair, and current and next frames as the other. From each of these image pairs, the eager motion network predicts the relative pose and rotation between the first and second image in the pair. If intrinsics are being learned, it additionally predicts the focal lengths fx and fy and principal points cx, cy as well. In our setup, the eager motion network can additionally estimate the intrinsics for the pair of images. Now, using the outputs of the depth and eager motion networks, we can reconstruct the current frame from the previous and next frames. This is done with the perspective projection equation where the source S is the current frame and target T can be the previous or next frame. The similarity between the current frame and its reconstructions are used to form appearance-based losses. These losses include a pixel-wise L1 distance loss and a structural similarity loss. Additionally, a multi-scale edge-aware smoothness loss on the depth is used to train the two networks. This figure shows a transformer-based method for self-supervised monocular depth estimation that we call Monocular Transformer Structure from Motion Learner or MTSFM Learner with learned intrinsics. First, we'll take a look at the structure of the depth network, for which we utilize a DIT base in the encoder, readapting dense prediction transformer that has been used for supervised depth prediction. It has 5 components. The first component is an embed module which is a part of the encoder. It converts non-overlapping input image patches of size P cross P into tokens of size D. For DIT base D is equal to 786. This operation is implemented as a P cross P convolution with stride P. We use P equal to 16 for all our experiments. The output from this module is appended as a readout token. The next module is the transformer block, which is also a part of the encoder. It has 12 transformer layers, which process the tokens from the embed module with multi-head self-attention modules. Multi-head self-attention effectively processes images at a constant resolution and can simultaneously attend to global as well as local features. Next come the 4 reassembled modules in the decoder. These modules are responsible for extracting image-like features from the 3rd, 6th, 9th, and 12th transformer layers. To do this, the readout token is dropped and the remaining tokens are concatenated in 2D followed by pointwise convolutions to change the number of channels as needed. Strided and transpose convolutions are used to downsample or upsample these features as required by the decoder. Next, we have 4 fusion modules in the decoder. These modules are based on RefineNet, a semantic segmentation network. These modules progressively fuse the information from the reassembled modules with the information passing through the decoder and upsample the features by 2 at each stage. Batch normalization is enabled in the decoder. Finally, we have 4 head modules in the decoder at the end of each fusion module. These modules predict pixel-wise depths at 4 scales, which are upsampled to the original resolution and used in the multi-scale edge-aware smoothness loss mentioned earlier. The table on the top right shows the architecture details of the head modules. Now, we move on to the description of our ego motion and Intrinsics estimation network. The encoder is again DEIT based, but with one major difference. As the input to the ego motion network consists of 2 images concatenated along the channel dimension, the embed module is repeated along the channel dimension. The decoder here only uses a single reassembled module. We adopt the decoder from monodepth 2 with 4 convolutional layers for our ego motion and Intrinsics estimation network. The 4th convolutional layer, without any activation, predicts the relative rotation and translation between the image pairs in the input. For Intrinsics estimation, we add a convolutional path from the 3rd convolutional layer before the value activation. This path contains a global average pooling layer followed by 2 branches. One branch predicts the focal lengths with a soft plus activation, as focal lengths are always positive. The other branch predicts the principal point without any activation. To test your transformer-based method, we perform a comparative analysis between our MTSFM learner architecture and existing CNN-based state-of-the-art architectures. All networks are trained on Kitty eigenslaw split, and we report the error and accuracy metrics on the Kitty eigensplit up to a fixed range of 80 meter depth. LR, MR, and HR here refer to low, medium, and high training resolutions, respectively. We observe that MTSFM learner is able to achieve comparable performance at all resolutions under error as well as accuracy metrics. This includes methods that also utilize heavy encoders such as ResNet 101 and PACnet. We also look at the performance of MTSFM learner on the Kitty Online benchmark for depth prediction. In the trained column of this table, D means depth supervision, SEG means semantic segmentation supervision, G means co-occurring GPS, S means stereo pairs, and M means monocular self-supervised training. The performance of MTSFM learner is on par with state-of-the-art self-supervised methods and outperforms several supervised methods. This further confirms that the transformer-based method can achieve performance comparable to state-of-the-art CNN-based methods. As self-supervised monocular depth estimation methods concurrently train depth and ego motion networks, we analyze the impact of architecture choice for each of these networks on depth estimation. The depth and ego motion networks can each be convolutional, represented by C, or transformer, represented by T. For transformer architecture, use DEIT base, and for convolutional architecture, use ResNet 101. It can be seen that the fully transformer method, that is MTSFM learner, performs best under 4 out of 7 metrics on Kitty eigensplit, while the remaining combinations perform comparably on all metrics. In addition to the quantitative results we saw earlier, we also look at qualitative results for each of these combinations. We observe more uniform estimates for larger objects like vehicles, vegetation, and buildings when depth is learned using transformers. Transformers are also less affected by reflection from windows of vehicles and buildings. This is likely because of the larger receptive field of the self-attention layers, which lead to more globally coherent predictions. On the other hand, convolutional networks produce sharper boundaries and perform better on thinner objects such as traffic signs and poles. This is likely because of the inherent inductive bias for spatial locality present in convolutional layers. Till now, we've seen that MTSFM learner performs competently on independent and identically distributed, that is IID, test sets. We also saw that quantitatively, the different architecture combinations perform comparably on such test sets. However, as models that perform well on IID test sets can still learn non-robust shortcut features, we analyze the impact of architecture choice on robustness. We first look at robustness to natural corruptions such as noise, blur, and weather change. As the figure demonstrates, there is a significant improvement in robustness to all natural corruptions when learning depth with transformers instead of convolutional networks. Now we look at the robustness to adversarial examples generated using projected gradient descent with respect to the training loss. We see that there is a general improvement in adversarial robustness when learning either depth or ego motion with transformers instead of convolutional networks. Finally, we look at the robustness to symmetrically flipped targeted adversarial examples. We again see an improvement in adversarial robustness when depth is learned using transformers instead of convolutional networks. Putting everything together, we note that MTSFM learner where both depth and ego motion are learned using transformers shows highest robustness across multiple tests. We attribute the higher robustness of transformers to their global receptive field, which allows for better adjustment to localized deviations caused by corruptions and adversarial attacks by accounting for the global context of the scene. Here, we look at the impact of a proposed modular method for self-supervised learning of camera intrinsics on both intrinsics as well as depth estimation. As seen in the table, the percentage error for intrinsics estimation is low for both architectures. Moreover, the performance on depth estimation when intrinsics are learned is similar to when ground truth intrinsics are used for training. We additionally probe the impact of learning intrinsics on robustness of depth estimation. We observe that robustness to natural corruptions and adversarial attacks is maintained by both architectures even when the intrinsics are learned. Therefore, a modular intrinsics estimation method is accurate at both depth and intrinsics estimation and is also robust. Furthermore, similar to the earlier scenario with known ground truths intrinsics, MTSFM learner with learned intrinsics has higher robustness than its convolutional counterpart. As these depth estimation networks can be deployed in self-driving systems and need to make inference in real time, we compare the architectures on computational and energy efficiency to examine their suitability for such applications. We report mean inference speed in frames per second and mean energy consumption in joules per frame over 10,000 forward passes. As seen in the table, both architectures run in real time with a mean inference speed about 30 frames per second. However, the transformer-based method consumes more energy and is more computationally demanding than its convolutional counterpart. To sum up, this work is the first to investigate the impact of transformer architecture on self-supervised monocular depth estimation. We demonstrate how to adapt transformers for the task with our MTSFM learner architecture. We additionally propose a modular method for self-supervised intrinsics estimation to eliminate the need for ground truth intrinsics and show that intrinsics can be learned without impacting depth estimation and robustness. Through a contrastive study, we analyze architectural choices for depth and ego motion networks, for trade-off between performance, robustness, and efficiency, and arrive at the following conclusions. In performance on standard benchmarks and in intrinsics estimation, CNNs and transformers are tied. Transformers are more robust to natural corruptions than adversarial examples. They also give more uniform depth maps and are better suited to dealing with large objects and reflections. CNNs, on the other hand, produce sharper outputs and are better suited to dealing with thin objects and boundaries. They're also more efficient. Thank you.